Welcome students, welcome to Basic Circuit course. The course code for this subject is EE93. I am your TA Prakhar Verma, and this course will be running for around 12 modules. Currently we are on the first module, that is a dry run, Module-0 to be precise. The timing for this class will be weekly, that is on Tuesday 6 p.m. to 7 p.m. and you can join using the Google Meet link as shown. So coming to the structure of the course, in today's class we'll be mainly dealing with simple basic electric problems related to circuit theory. So during this session you can type your questions, any doubts, I'll be answering them. Besides that, I will also be solving some questions, basic electrical circuit related questions. So the video for today's class will be also available on YouTube. The channel link will be shared at the end of the class. Also, I will share it on the chat box. So let's begin. So beginning our tutorial for today, that is module 0. So first question here is, current of 6 ampere flows in a resistor. How many coulombs of charge pass through the resistor in 2 minutes? So as per the question, we are given with a resistor through which a 6 ampere of current is flowing. So the examiner wants us to know that how many coulombs of charge pass through the resistor in 2 minutes. That is from time 0 seconds to time 2 minutes, that is 120 seconds. How much coulomb of charge passes through this resistor? So as you all know that current is nothing but instantaneous flow of charge coordinate time. So from here we can write that dq is equal to I dt, taking integral both sides. So here the time limit is from 0 seconds to 120 seconds, and for charge supposed to be that the resistor doesn't hold any charge, so it was 0 coulomb, and after time 120 seconds it holds a charge q. So integrating this side, we get q limit 0 to capital Q is equal to I. Again, I is here given as a constant quantity, so we'll replace the value of I here as a constant value, that is 6 ampere. So I'm just substituting I to be 6 ampere, and time, again dt, time is integral, then the lower limit is 0 seconds and the upper limit is 120 seconds. So on the LHS side it comes capital Q, whereas in the RHS side this becomes 6 into 120 minus 0. Again I'm solving this step by step just to clear all the doubts. So 6 multiplied by 120, so this becomes 720 seconds, sorry 720 coulomb. So total of 720 coulomb of charge passes through this resistor. So the correct answer should be D, 720 coulombs. So yeah, 720 coulomb is the right answer. If you have any doubt regarding this question, you can post your messages in the chat box. So now moving to next question, that is question number 2. The potential difference between conductor is 110 volt, and how much work is done in moving a 5 coulomb charge from one conductor to other? So again here they are saying that there is a conductor, so there is a conductor and the potential difference across two terminals is 110 volts. So how much work is done in moving a charge of 5 coulomb from one conductor to the other? So again, you know that work is defined. The potential difference is here defined as the work done per unit charge. In simple terms, we can say total work done is equal to potential difference multiplied by the total charge. So here they have already provided the potential difference across the two terminal, that is 110 volts, and the charge is 5 coulomb. So again, multiplying these two terms, these are simply straightforward questions. So 550 joule is the correct answer. So it should be B, 550 joules. Okay. So again, moving to the next question. These are simple questions and should be solved. Typical MCQ type question. So the third question is voltage and the current in the circuit element are given. So voltage they have provided as 100 square root 2 sine t hertz, and the current is 5 square root 2 sine t amperes. So we have to calculate the average power delivered to the circuit. So again, we know that average power P average is equal to potential difference V average multiplied by current average into the power factor of the circuit, that is given by cos theta. So now we have to understand here that the value, this value given here is not the average value, but this is the peak value. So for example, if we have given the waveform for potential V, so this value they have provided, that is the peak value, that is 100 square root 2. So we have to calculate the V average value. So again, if we already know that V average for our AC system will be 0. So in V average value here is 0. So that is why we are not taking the V average, but we are interested in V RMS value. That is the root mean square value. So the root mean square value is given by V voltage peak voltage divided by square root of 2. So this V RMS becomes Vp, that is peak value, 100 square root 2 by root 2, that is simply 100 volts. Similarly, the IRMS value can be similarly calculated. So this is again given 5 square root 2. So again dividing it by root 2, we get 5 amperes. So now substituting these two values. So just to clarify here, these are not average values, but these are RMS values. Because in case of a AC voltage waveform, the average will be 0. As you know that in the area of this positive and the area of the negative is equal, so this will cancel out, so the average value becomes 0. So that is why we have to consider the RMS value. So now we are just substituting these values here. So the RMS value for voltage is 100, and similarly the RMS value for current is 5 amperes, and cos theta, so cos of angle theta, theta is the angle between voltage and current. So here, as these are provided, these are sin t and again sin t, so there is no phase difference. So a no phase difference means that the angle between them is 0 degrees. So this becomes 100 into 5 into 1, cos of 0 is 1, so this becomes 500 watt. So again, this is the active power, so the unit has to be watt. Again, if there was some reactive component of this circuit, then we can also found out the reactive power, that will be Vrms, Irms, sin theta that is the other part which is reactive component. So in current case, average power was to be delivered to the circuit comes out to be 500 watts. So 500 watts the correct answer. So I will request all the participants to please and put their answers in the chat box, and also if there is some confusion you can write it in the chat box. So moving to question number 4. So question number 4 says a cube of an alloy of resistivity 1.12 micro ohms meter is 2 centimeter on a side. So we have a alloy that is basically a conductor which is having a resistivity. So this, suppose this has to be a cube. So this is a cube, and across this cube we need to find the resistance between the two ends. That is, suppose this is point A and this is point B, so we need to find the resistance. So again we know that resistance R is nothing but directly proportional to the length of the alloy or a conductor. It is this length divided by the area, surface area. So this is, in this case, this is the surface area. So we can say that the surface area here representing this region, and similarly the proportionality constant becomes rho. So R is equal to rho L by A, where rho is the resistivity. Again, just to define rho, so rho is a property which is not dependent upon the dimension of the resistor, of the conductor or a resistor. So rho is completely independent of dimension. This is completely independent of the dimension, not related to the length or the thickness. But what rho is a function of temperature. So we have to remember this thing. Rho is a function of temperature, but rho is not a function of dimensions. So anyway, our problem is not related to that. So the resistance here, R, can be calculated. So rho is given 1.12 micro ohms, so 10 to the minus 6 ohm meter. So length between these two nodes is 2 centimeter. So 2 into 10 to the minus 2 meters. And the area, so since this is a cuboid, all sides are of 2 centimeters, 2 into 10 to the power minus 2 into 2 into 10 to the power minus 2 meter square. So this term gets cancelled, and we are left with, so just let me make some space here. Yeah, so we are left with 1.12 10 to the power minus 6 divided by 2 into 10 to the power minus 2. So just send this to above. This becomes 10 to the power, sorry, 10 to the power minus 4. 10 to the power minus 4, and dividing this by this, so this becomes 5 and 6.56 into 10 to the power minus 4. So this will be 56 10 to the power minus 6 ohms, that is 56 micro ohms. So 56 micro ohms, A is the correct answer. So again, keep your calculators handy. So you can always use a calculator to do this kind of simple calculation. You don't require this much hand calculation. So the answer is 56 micro ohms. So moving to the next question. So again, this is a straightforward question. A resistance of 2 ohm and 5 ohm are connected in parallel, and we have to calculate the total current supplied by a 12 volt source connected across the combination. So just I will be solving this question step by step. You can input your answer on the chat box. So we have two resistors, one is of 2 ohm, the other resistor is of 4 ohm, and the circuit is being connected by a voltage supply of 12 volts. So calculate the current supplied by, so we have to calculate the total current I. So again, this is a straightforward question. We will be writing voltage is equal to current into total resistance. So total resistance, this is a parallel circuit, voltage is 12 volts, and current you have to calculate the total current I. This is a parallel circuit, so therefore R equivalent, this R equivalent has to be calculated. This R equivalent becomes, so I'll just use the shortcut, that is R1 into R2 upon R1 plus R2. Again, this is a very fairly simple question. I will want to discuss why this is. Okay, so this becomes 2 into 4 upon 2 plus 4. So that is 8 by 6 or 4 by 3. So putting this 4 by 3, so I becomes 12 into 3 divided by 4. So this is 9 amperes. That is 3 and 3 by 3, 9 amperes. So 9 amperes is the correct answer. So just for clearing all other doubts, some problems related to this can be, we may have to find the current from each resistor. So I'll just put the shortcut formulas here. So suppose we have to calculate current I1 or I2. So current I1, so what fraction of current will be I1? We have to say, so the total current is 9 amperes. So how this 9 ampere of current is getting divided in these two circuits? So as you know, the lower resistance will be having higher current since the circuit is in parallel. So we can simply write the current in the 2 ohm resistance should be 4 ohms. It is the other part resistance, that is R2, divided by sum 2 plus 4 into the total current 9 ampere. So this becomes 4 by 6 into 9. So 3, 2 and 2, so 6 ampere. 6 ampere will flow from here, and the rest 3 ampere from here. So again, to recheck, the voltage should be same in both the branches. So in the upper branch we have current of 6 ampere and resistance is 2 ohms. So 6 into 2, that is 12 ohm. Sorry, 12 volts. That is a 12 volt supply. And again 4 ohm into 3 ampere, 12 volts. So again, this is a shortcut technique. Is the other resistance R2, we have to calculate the current from R1. So this is current from R1 is R2 by R1 plus R2 I total. Okay, so moving to next question. The next question is related to inductor. A 40 millihenry inductor is connected in parallel with a 60 millihenry inductor and with a time varying voltage source. At a certain instant, the total current supplied by the source is 10 ampere. Determine the current through the 40 millihenry ampere. Again, this question is similar to the previous one. Instead, we are having inductors here instead of the resistor. So again, we have a parallel inductors. So first of all, we can say that The upper inductor is of inductance 40 millihenry, the lower one is of 60 millihenry, and total current source have also provided that the current source is being attached. No, so there is a time varying voltage source and they have provided the value of current. So we are having a time varying voltage source. So this is a time varying voltage source in AC source that varies with time, but the current I is given here as 10 amperes. So we have to calculate the current through 40 millihenry ampere. Again, so since the impedance is L omega, so we can treat this Z again using the similar formula for resistance we used. So if we want to find the current for the 40 millihenry branch, so this is just a notation I am writing here. So this is current from 40 millihenry. So we can write this as 60 millihenry, that is 60 to the power minus 3 Henry into omega by, similarly, 40 plus 60 10 to the power minus 3 omega into the total current I. I is given 10. So this again becomes 100, this part and this part gets cancelled out, so becomes 100 into 60 into 10. So just simplifying 0, 0, 0, 0, so this becomes 6 amperes. So 6 ampere of current should flow through the 40 millihenry inductor. Okay, so 6 amperes of current is being flown from the 40 millihenry node, branch to inductor. So coming to the 7th question. So the 7th question says the current through a 200 millihenry inductor is given by this expression. So this is the expression, that is current is a function of time. And so what is the energy stored in the inductor after 1 second? So the supply is, you have to understand the supply has been resumed at 0 seconds. So from the time period 0 to 1 second, how much of the energy is being stored in the inductor? So energy we know is V into I into dt integral, where time period is t1 to t2, time, that is t1 to t2 time period for which the inductor was being charged. So again we know the inductance, that potential difference is directly proportional to the change in current, instantaneous change in current. So that is given by this expression. So we'll be substituting this expression in this equation. So it becomes, time is from 0 to 1 second, voltage is being replaced by L into di by dt into I into dt. So we can cancel out dt. So this becomes L. We can take, the L is constant value, so we can take L outside, integral I di. So again now the limit for this integral has to be changed, because now we are integrating with respect to current. So when we are integrating with respect to current, so the integration should be also over current. So as given from the expression, for 0 second the current will become 2 e to the power 0 minus 2 e to the power 0. So this becomes 2 minus 2, that is 0. So 0 ampere of current is at time 0. And finally at 1 second the current is 2 e to the power minus 1 means 2 e to the power minus 2. So again you have to keep your calculators handy here. So I will just using calculator here. to find the values. So I'll just put in the numbers 2, divided by E minus 2 divided by E squared. So the value is 0.465 amperes at 1 second. Okay. So just substituting these values, that is 0.465 amperes. So integrating this, L value is 200 10 to the power minus 3. This becomes I square by 2, 0.465. So again, just rubbing this portion, and we can write it out. 200 10 to the power minus 3. Current becomes 0.465 by 2, and this being squared. So 0.465 in 0.465 into 0.465 divided by 2 multiplied by 0.2. So this comes out to be 0.0216 joules. So that is 21.6 joules. So 21.6 joule. A. This is the correct answer. So moving to question number 8. You can all post your doubts. The question number 8 says a 40 millifarad capacitor is connected in parallel with a 60 millifarad capacitor with a time varying voltage source. At a certain instant of total current supplied by the source is 10 ampere. Determine the current through 60 milliampere. Okay, so this is a question similar that we attempted with inductors, but here they have replaced inductor by a capacitor. So again, just sake for clarity of the question, we'll be drawing the circuit. So total current is 10 ampere and capacitors are 40 millifarad and 60 millifarad. So now the Z1 will become 1 upon C omega, that is 1 by 40. So millifarad is there, so I'll just sake of simplicity I will not write in millifarad because ultimately those millifarad things will get cancelled. So that is why I will not be writing at millifarad. So this becomes 1 by 40 omega and Z2 becomes 1 by 60 omega. So we have to find the current through 60 millifarad. So this portion we have to find as current. So again, I for 60 will be taking this value Z1. So 1 by 40 omega upon sum 1 by 40 omega plus 1 by 60 omega and multiplied by the current, is 10 amperes. Okay, so just taking the LCM downwards, this will be 60 omega 40 omega multiplied by 40 into 60 omega square, and in the numerator we have 1 by 40 omega whole multiplied by 10 amperes. So in the denominator we have 100 omega, this goes up, 40 omega gets cancelled, we have 60 omega divided by 10 Omega omega gets cancelled, these two zeros, 0 and 0, so this simply becomes 6 ampere. So a 6 ampere of current should flow through 60 millifarad. So 6 ampere of current is flowing. So again, just to clarify your doubts, the capacitor with high capacity allows more current, whereas a resistor or an inductor with low resistance allows more current. So this basically is because capacitance is the reciprocal. Is in the reciprocal. The impedance of a capacitor, the capacitance comes as the reciprocal, that is in the denominator form. So that is why a high capacitor draws more current as compared to resistor or inductor, which does opposite. Now moving to our ninth question. So in the ninth question, a 46 millihenry inductive coil has a resistance of 10 ohm. Okay, so this is a coil, so this is not a perfectly ideal inductive coil. So this is coil which is having some resistance. So determine the power factor of this coil. So suppose this is a practical coil, that is not ideal coil, practical coil. So for a practical coil, this can be transformed into an ideal coil with a series of resistance. So now this becomes an ideal inductive coil with 46 millihenry of inductance, and the resistance here is 10 ohms. So again you have to calculate Z, that is the total impedance. So Z will be R plus JL omega. Now omega, there in the question the value of omega is not provided. So in such cases we have to take a default value, that is, we know omega is equal to 2 pi f, where f is the frequency of the AC supply. So in India we are having 50 hertz of AC supply, so we'll be taking f equal to 50 hertz. So omega becomes 2 pi into 50, that is 100 pi. Okay, so they haven't mentioned this value, we have to take this as a default value. So just putting those values here in the expression, 10 ohm of resistance, J, inductance is 46 10 to the power minus 3, and omega is 100 pi. So this becomes 10 plus J 4.6 pi. So power factor is nothing but cos theta, and theta is here the angle between the resistance and the inductance. So the resistance is 10 ohms and inductance is 4.6 pi ohms. So the equivalent Z value comes out somewhere. So this angle theta, so that is nothing but cos theta, where has to be. So for this we need to calculate the value of theta. So theta will be tan inverse the perpendicular by the base. Perpendicular is 4.6 pi, base is 10. So theta becomes, again we'll be using our calculator. So tan inverse 4.6 into 3.14 divided by 10. This is 0.965. So cos of 0.965 cos of 0.965 becomes 0.56. So this power factor comes out to be 0.5. The decimal up to only one decimal point. That's it. And the second question is whether this is lagging or leading supply of 0.5 power factor. So since this is an inductor, so in case of an inductor, the current always lags behind the voltage. So that is, if this is representing voltage here, so the current will be always lagging. So that is why the answer A has to be there. That is, the current is lagging the voltage by 0.5 power factor. And similarly, in case of a capacitor, the current will be leading. So that is why we have capacitive banks to improve the power factor of the circuit. And for example, induction motors. So the induction motors have this inductive coil, so therefore this draws huge amount of reactive power, and we have a lagging supply. That is, the power factor lags. That is, the current basically lags behind the voltage. So finally, we'll be moving to our next question. That is question number 10. So this will be the last question. So again, we have two impedances. Okay, so the first impedance is 2 plus J4. That is, we have a resistor as well as there is a inductor, 2 ohms and 4 ohms connected in parallel to a resistor of R ohms. So determine R so that the power factor of the circuit is 0.9 lagging. So obviously the circuit will be lagging because we have an inductor in the circuit. There is no capacitor, so there is no chance that the power factor will be leading. So we have to get the power factor, that is cos theta they have provided as 0.9. So we calculate tan theta because tan is significantly simpler, as you can just do the perpendicular by base and calculate this. So again, we'll taking the inverse of the cos. So cos inverse of 0.9 is 0.45, and then taking tan. So tan of 0.45 becomes 0.48. So we know tan theta. Now let's come to the circuit. So coming to circuit, we know for this circuit we can write 2 plus 4j is in parallel with resistance R. So the equivalent resistance Z, impedance Z, becomes multiplication by sum. Okay, so 2 plus 4j into R divided by 2 plus R plus 4j. Now we have to rationalize this because in the denominator term we have a imaginary part, so again multiplying by the conjugate 2 plus R minus 4 of j by 2 plus r minus 4 of j. In the denominator we have 2 plus r whole square minus 4j whole square, so j square is minus 1, so plus 16 whole square, it is 16. In the numerator part we have 2r multiplied by 2 plus r, and again this part j into j part will be again a real number, so plus 4 into 4 16 r, this is the real part, and plus the imaginary part 2 plus r whole square plus 16. Imaginary part is 4r into 2 plus r, so this is a whole j part here that I'm going to write here, so this term is gone. 2 plus r into j. Okay, everything is done now. 4j r multiplied by 2 plus r. The other 2r term has, this term has already been multiplied here, and so hopefully I am doing this right. 2r 4rj, so 2r multiplies with the real part, and 4gr multiplies with minus 4gr become positive. 2r multiplied with this, yeah, so that term was forgetting, so it will be minus 2r into 4. Okay, minus 2r into 4. So this is the real part, this is the imaginary part. We know tan theta is 0.48, so 0.48 is equal to imaginary by real. So again the denominator part is going to get cancelled in the form, so we're going to write interested in the numerator part, so that is 8r plus 4r square minus 8r divided by 4r plus 2r square plus 16r. 8r goes out, 4r square above 2r square plus 20r. So taking 2r common, this becomes r plus 10, and above this becomes 4r square, so it is 2r by r plus 10 equal to 0.48, so 2r minus 0.48r is equal to 4.8. So 2r minus 0.48r, 2r minus 0.48r, just clear here, 2r minus 0.48r is 1.52r equal to 4.8, so r becomes 4.8 by 1.52. 4.8 on 1.52. 4.8 divided by 1.52, 3.15. So this is around 3.158. That is 3.2. Nearest answer, closest answer is 3.2. So just checking, yeah, so correct value is 3.2. So this was the last question for the module 0, that was for the dry run module 0. So on August 2nd of August we will be having our first module, module 1. Kindly join on Tuesday from 6 p.m. This will be a 1-hour session. The Google Meet link is being provided. Also, uh, the video recording of this lecture will be available on YouTube, and on YouTube you can search the channel NPTEL electric circuit. I will provide the link, don't worry. And also these questions and solutions will be available on the Google Drive link. So these links will be provided to you. So see you on 2nd of August. Till then, take care. I'll be ending the meeting now. Thank you.